Dear researchers, stop trying to monitor wildfire progression using the sensors that can't even see through the smoke. During massive forest fires, optical satellites become blind beneath dense smoke and the atmospheric disturbance. But radar satellite never stop observing. Using Sentinel-1 SAR coherence change detection and the SARscape CCD Timeline Workflow, we can monitor the wildfire progression through smoke, cloud, and the darkness. Most wildfire monitoring system still depends heavily on the optical satellite imagery. But during major wildfire events, dense smoke can completely block visibility. This creates several problems: hidden forest fronts, delaying burn mapping, inaccurate fire extinction estimation, and the poor temporal monitoring. Optical sensors become almost blind during the most critical stage of the wildfire progression. However, SAR operates differently. Since SAR uses microwave signal instead of visible light, it can penetrate smokes and clouds and continue observing the Earth's surface continuously. Okay, so the key question become: can we monitor wildfire progression even when the smoke hides the surface? Most importantly, can we detect not only the fire location but also the fire spread direction, active fire fronts, temporal expansion, and the post-fire stabilization? This is where SAR coherence become extremely powerful. Why is synthetic aperture radar? Synthetic aperture radar SAR is an active remote sensing system. Unlike optical sensor, SAR actively transmit microwave energy toward the earth and record the returned signal. This gives SAR several major disadvantages: day and night acquisition, cloud penetration, smoke penetration, and high sensitivity to surface structural changes. These properties make SAR heavily suitable for wildfire monitoring and the temporal change detection. Uh, let's understand SAR coherence. Now, it is the most important concept in this workflow. SAR coherence. Coherence measures the similarity of the radar scattering between two SAR acquisition dates. High coherence indicates stable surface, minimal structural change. Low coherence indicate temporal variation, disturbance, or the major surface change. Urban regions usually produce high coherence because buildings remain stable. Vegetation, however, naturally produce lower coherence due to constant structural variation. Uh, why forests naturally decorrelate over time? Even when the forest appear visually unchanged, the radar scattering changes because leaf moves, branches sway, moisture content changes, and canopy structure evolves continuously. These effects create the temporal decorrelation. As a result, healthy vegetation generally appears with low coherence in the SAR interferometric analysis. Uh, Now let's examine what happened during the active wildfire progression. As the fire spread, vegetation burns, canopy structure collapse, and soil become exposed. This dramatically changes the radar scattering mechanism between acquisitions. So during the active fire expansion, forest to burn transition produce very low coherence. This is an important concept. First, fire itself doesn't immediately create high coherence. Instead, active burning usually causes strong decorrelation. Okay. Uh, After the wildfire stop spreading, the situation changes again. The burn surface become relatively stable. Now the radar is observing observing exposed soil, ash covered terrain, and the reduced vegetation moment. When two post-fire images are computed, the scattering mechanism becomes more similar. As a result, one-to-one image pairs often produce high coherence value. That is, this is the coherence recovery stage after a wildfire disturbance. Okay, the SARscape coherence CCD timeline workflow automates the entire process. The workflow include image co-registration, interferometric pair generation, coherence estimation, and the RGB temporal composition. Each coherence pair is assigned to the RGB channel, red, green, and the blue. This transform temporal coherence information into the visual fire progression map. What I mean is that is, okay, let's say this is one image before forest fire image. This is image that at the early stage of forest fire. This is image during the forest fire, and this is an image at the last of the forest fire. Okay, there is the coherence is totally dissimilar because there is the forest fire automatically the forest leaves create the coherence low, as well as if there is a forest fire here in this area, the area is totally different. But if we come to this area, right, and there is already a forest fire in the imagery, and there is a new, right, and if you observe this region and this region, the coherence is same. The site is stable, so that the coherence is high. So we can accept red value, right? And in this image, let's say this is the first image where the coherence is same. This is the image where the coherence in the second image, and this is the new area, right? And at this point and this point, there is the coherence is same. So here you can see here in this portion there is a green value, right? And in this portion here this has a red value, already red value. So there is a mixing of red and green, and you can see sign value, right? This is how the CCD workflow works. Okay, and the RGB composite allows us to interpret the different wildfire stages spatially. Different color represent different temporal coherence behavior. For example, black region often indicate unburned vegetation. Cyan region may represent the earlier burn zones. Blue regions often correspond to later burning, and the white region usually indicate stable burn surface across multiple dates. So instead of simply mapping burn scars, we can visualize the temporal evolution of wildfire spread. SAR-based wildfire monitoring provides the several major advantages: smoke penetration, cloud-independent observation, nighttime acquisition capability, rapid temporal analysis, and large-scale disaster assessment. These advantages make SAR extremely valuable for operational wildfire intelligence system. The future of wildfire monitoring is moving toward near real-time SAR processing, AI integrated coherence analysis, automated fire progression detection, and predictive disaster intelligence system. Combining SAR, GeoAI, and temporal analysis can significantly improve disaster response and environmental monitoring. So the next time smoke blinds optical satellite during a wildfire disaster, remember this: radar continuous watching. So let's move to the actual tutorial how we are going to mapping this. Thank you. At first, you must have an area of the interest of that particular locations. Here I have already created my area of the interest in the Google Earth. Here you can see my area of the interest for the forest fire that is displayed in the Google Earth Pro here. and I'm going to do an analysis of this forest fire for the northern Australia, and you can visualize my area of the interest over the Google Earth Pro. You can check the location, and I'm going to download the Sentinel-1 imagery of that particular locations from the Alaska site, and go to your search bar and search for source.asf.alaska.edu. You can see the canvas of the data or the canvas of the site here, and I'm going to upload my KMZ file. Okay, just go to the section, and yeah, at this I think the KMZ doesn't accept here, so I'm again go to the Google Earth Pro, and I'm going to right click over here and go to the just I'm right click over this file and go to the save place as, and change the file type to KML and save over the inside the download section. And I'm going to go to the Alaska site and hit over the import file. At this time I'm going to choose the KML file. Okay, just I'm selecting the first KML file and click open and it is successfully imported, and the map is directly focused to that my area of the interest. Okay, and click over the filter button, and I am giving starting and the end date, and I'm going to download all the data set. At first go to the file type, and I'm going to download the SLC data type and file, and it is IW and and I'm not selecting the polarization, and I'm order is in descending orbit. Here you can see that all of the files are displayed over the regions, and I'm going to download that only imagery that contain most part of our area of the interest. And here you can see in the red box, if you click over the imagery, you can see the reach ROI is covered with the red polygon, and click over the download buttons. And, you need to log in with your own credential to download, and I'm applying mine, and it will automatically redirect to the download sections. And I am going to download all of the imagery, right? Before I'm going to download one imagery, that is before forest fire, and two imagery during forest fire, and the one is after forest fire. I'm going to do this analysis over the NB, so I'm opening my NB 6.2, and you can see okay. And at first we have to open the Sentinel-1 imagery and go to the SARscape and go to the SAR spaceborne single sensor and click over the Sentinel-1, and inside the input file you have to give all those input files. Click over the open, and the optional file you have to give your own area of the interest, and mention your folder to keep those all of the open file. And this open file contains lots of the information, so create your own empty folder and save all these files inside that particular folder, and click over the execute, and your process of opening will automatically started. And here in my screen it is already started, and within a minute you can see all of these open data in my map canvas. Okay, just wait for a minute, and I think within a minute I will find all these imagery inside my canvas. That's all. Here you can see all of the imagery is loaded one by one. One thing is we are only open 4 imagery, but you can see the 8 layers because each imagery contains the 2 bands, that is VV and the VS bands. And here in this tutorial we are only using VV bands, and you can see the difference in each imagery according to its nature and the time. And you can see the difference in the surface due to the forest fire and due to the BB and BS bands. That's all, and you can zoom in and zoom out the imagery to see the full portion here. And we are using the CCD timeline workflow, so go to the toolbox and search for CCD, and you can you get the coherent CCD timeline and the PWR. And there are some warnings while opening, and I'm going to I think there is it doesn't cover much specific details, so I am simply closing this warning. And it first go to their browser section and navigate to the folder where you keep all these open folder. I think I'm keeping over the forest fire, and I'm only selecting the BB bands because I can mix the BB and BS band. And you have to go to the DEM cartographic section. I'm going to using that DEM that is automatically downloaded in this portion. And okay, input section is over. Import generic SAR data, you leave those principal parameters, and multiple coherence, change the range looks value to 4. And okay, everything is perfect. Coherence geocoding, everything yes, and it will produce the resolution of 15 to 15, so you can leave all those parameters. And from in the generate color composite operation, you can select the standard RGB in the imagery and mention the folder where you are going to keep all these results. And I'm going to same folders and I want to create the one new folder with the name results, and I'm making the one folder result, and I'm saving with the same value. Okay, hit over the next button, and your CCD timeline workflow is automatically get started here. You need to wait for some minutes. Sometimes it will take some time, even 2 or 3 hours. I am making this video much faster for to show all of the process one by one. And input in the workflow, your input is successfully inputted in the workflow. And here we comes to the import generic SAR data. Importing SAR data, importing generic SAR data is also completed. Here I miss write as 3, and you can write to the range. You have to give the range looks to 4. And if you are want to know the what actually happening inside this process, you can visit my website, and there I have mentioned all of the theory behind this, and you also get some of the theory in my first theory part. And at this time multiple coherence is started here. You really need to wait some minutes, some hours, based on your computer. And I think if you put all of the information corrected, you have to do nothing while the workflow is completed. It's the best part of this SARscape workflow. So multi-temporal coherence is completed, and now it comes to the coherence geocoding. What the geocoding done is at the originally SAR data is not geocoded, and using the geocoding tool you can geocoded the SAR imagery and getting the result in the SAR in the actual geospatial format, right, in the geocoded format. And if you overlay this result with the actual map, you can get your result overlay with the imagery. And at last, after completing all of the step, you go to the you are redirected to output. If you click over the finish button, and you can see the most attractive forest fire mapping here in your screen. Just cancel the workflow. I think I get some of the error, so I have to okay, now just wait a minute. I have to warning, and I'm clicking over the OK. My workflow is gone, so I have to regenerate my but all of my results are saved here, but I have to clear the color composite again. So I'm going to go to the toolbar and search over the click and the generate color composite in the inside the result folder. Here you have to give the ccgo file is the 3 input file. No need to keep anything else. Operation type is standard. I'm going to produce this result in the RGB format. So go to your same folder and okay, and at this time inside the go to the result folder. I am going to give this name as the RGB because I am going to derive the results in the RGB format, and hit over the execute button. It will take much less time, less than 1 minute to execute this process. And okay, just wait a minute. Here you can see that our result is completed, and you can interpret the result as mentioned in the theory. The cyan portion early forest, blue later, white the stable already born area, and the black portion the area that is not affected by the forest fire. So if you can go to the reference map link, you can see your result in the reference map link. Okay, if you are interested to generate this result in the other color option, there is also the SARscape facility us to generate same result in the different color format. And so to visualize it in the different, and you have to give the input to the same ccgo files. And at this time in the parameters, in the option type, you have to select the MICCD. It is the standard format that for the fire detection. So I'm going to I'm browsing to the same folders, but at this time I'm going to name it as the MICCD, and click over the open and hit over the execute. Will take a time, but it will definitely get us the result. Okay, it is generating the result in the much pleasant color format. You can see here, but if you want to make it much clearer, so change the stress types to linear 2%. You can see the results in much clear version. Here you can change this image also to the linear 2 format so that you can visualize the image. Yeah, and that's all from my side, and you can generate the result something like that and interpret from my side. Thank you for watching, and thank you. Bye bye.